We are Team 25075, the Sparkling Sunbeams. Demand for renewable energy is growing. Microgrids improve resilience and address aging infrastructure by combining renewable sources and energy storage. Hydrogen is an emerging storage solution, offering greater efficiency and sustainability than traditional batteries.
Our project designs a Tucson neighborhood microgrid that relies on photovoltaic input and is firmed by hydrogen technologies. By combining solar panels, an electrolyzer, hydrogen storage, and a fuel cell, the microgrid can provide energy to residents under any weather conditions. The project models a distributed energy resource management system. These models visualize energy flows and address challenges of widely fluctuating energy inputs and load requirements.
In this video, we will outline the challenges with a microgrid system, how our system solves these problems, the technical aspects of the design, and the safety, economic, environmental, and cultural impacts of the project.
First, let's outline the problem presented by utilizing renewable energy to power a neighborhood. Here is the load demand, or how much power the neighborhood needs over the course of the day, visualized. As you can see, the load peaks in the morning and declines over the day. However, this peak of demand changes over the year. This is affected by things like heating and cooling, along with appliance use. This ridgeline graph shows this variability. The peak demand does not occur at the same time every day and changes drastically throughout the year.
The solar power produced throughout the day is displayed here. This shows that the peak of solar production starts around hour 10 and stays steady till around hour 15. Similar to the load, peak solar production changes throughout the year.
Solar production doesn't align with peak neighborhood demand. Microgrids typically solve this with battery storage, saving excess solar energy for later use. But batteries face challenges, such as high upfront costs, limited raw materials, and long-term degradation.
Our project aims to address this energy storage problem by utilizing excess solar energy to produce hydrogen gas. This hydrogen gas is stored and then input into a hydrogen fuel cell to produce energy to meet demand when there is no solar power available.
Here you can see the hydrogen gas our design produces throughout the day. The production of hydrogen gas coincides with the time when there is excess solar energy being produced.
As the load demand rises and solar power production falls, the hydrogen fuel cell utilizes hydrogen gas to produce energy. This energy production from the hydrogen fuel cell can be seen in this graph, continually meeting the demand load without solar energy.
Our team chose to model our microgrid on a 19-home Tucson residential neighborhood.
For the system to run entirely off the grid, a massive amount of solar energy needs to be harnessed in order to power the load, electrolyzer, pumps, compressors, and charge the batteries. 4,400 meters squared of solar panels are required.
The electrolyzer uses excess solar energy to convert water into hydrogen and oxygen using electrolysis. The proton exchange membrane technology uses a solid polymer electrolyte membrane to facilitate the passage of hydrogen ions from the anode to the cathode. The electrolyzer uses 650 liters of water a day, operating at a conservative 60% efficiency to produce about 72 kilograms of 99.99% pure hydrogen a day, or an equivalent of about 3,900 kilowatt hours per day.
After hydrogen gas is produced by the electrolyzer, it is stored in a 10.5 meter cube stainless steel and composite tank. This tank is pressurized to 700 bar and operates at 80 degrees Celsius. The pressure and temperature regulation is done by compressors and a heat exchanger system. Safety is key when it comes to hydrogen storage. The storage is designed following OSHA 1910.103 regulations. The safety features include pressure sensing and automatic shutoff and release if an issue occurs.
When solar does not produce enough energy for the load, a PEM hydrogen fuel cell uses a hydrogen from the storage and oxygen from the air to produce energy using the hydrolysis reaction. The fuel cell is sized to produce a maximum of 338 kilowatts at any given moment. PEM fuel cells transform the chemical energy from hydrogen and oxygen into electrical energy. Each fuel cell contains one or more membranes that act as ionic conductors, allowing hydrogen ions to move from anode to cathode.
One problem facing the utilization of a fuel cell is the response time. When a light is flicked on in the house while the fuel cell is providing most of the power, it can take up to 200 seconds for the fuel cell to kick on. Therefore, a small group of lithium-ion batteries are implemented to run for 200 seconds every time the power draw switches from the solar panels to the fuel cell.
After energy is produced by both the solar panels and the fuel cell, the current must be converted to AC in order to be used by the grid. The inverters are sized to handle the maximum energy production at any time in the day.
We implemented an innovative water recycling system that reuses utility water from all heat exchangers and water produced by the fuel cell. This closed-loop system cut our water usage from 3,800 to 400 kilograms in 3 days, resulting in an 89% reduction.
Software is not readily available to design this project. Therefore, the team designed each piece of equipment in Excel with all design variables and constraints linked across sheets. This allows for the load and solar panel area to be input, and it will size the electrolyzer, storage, fuel cell, and more. This Excel is modular and adaptable, able to be utilized for any site or application.
With the system fully designed, the team modeled how the microgrid would react under real conditions. Taking real load requirements and real solar irradiance data, the team developed a MATLAB script that utilized conditional logic to map the energy flows throughout the system. The script takes into account the efficiencies, power requirements, and power outputs of each unit op, calculating and then visualizing the energy throughout the entire system. Calculations done by the script were also used to optimize the size of the battery and fuel cell.
The model is modular, scalable, and interactive. Each individual system component is represented, and other engineers could use the tool to model their own microgrids, inputting new solar and load data for their specific application. The interactive design allows users to push their systems to extremes, visualizing real-time system response to varying conditions.
The system has a total capital investment of $2.9 million and has an annual operating cost of $192,000 a year. Utilizing a conservative 30-year lifetime, the net present value is negative $4.18 million. To break even on this project over 30 years, the energy cost would be $1.19 per kilowatt hour. This is about 9 times the current cost of energy. However, the benefits of a self-sustained microgrid are not directly comparable to the fossil fuel-dependent grid we live on today. Innovative energy projects often rely on grants or investors to be successful. The cost is also expected to decrease as production of hydrogen technologies increase.
When looking at hydrogen systems, safety is typically the number one concern. Hydrogen gas is highly flammable and makes the proposition of hydrogen-based fuel systems scary to consumers.
However, when hydrogen systems are designed and operated correctly, risks are minimized and the result is a safe system. Key safety features found in the system are ventilation, leak detection, pressure regulation, and flame arresters. The team developed hazardous operations assessments for each unit found within the system and developed a health and safety plan that contains PPE requirements, hazards, and regulations.
Community outreach is key to informing the residents surrounding the system. The team developed a series of safety walkthroughs and educational demonstrations to build trust.
Through innovative design and implementation of unique modeling techniques, the team proves the viability of a hydrogen-firmed microgrid in Tucson, Arizona, while considering the safety, economic, and environmental impact of the system. Hydrogen energy storage effectively addresses the intermittency of renewable energies more sustainably. This can be applied to different microgrids for different needs in the future.
The future of energy is in sustainable, decentralized solutions, and microgrids like ours pave the way for a cleaner, more resilient grid.